Good morning, Chichuni. Good morning, everyone. So, have you revised the previous lecture? My voice is clear now? Have you revised everything of the previous class? What we have studied in the previous class? Can anyone tell me the last topic that we have covered in the previous class? Last topic of the previous class? Biasing. Okay. Okay. So, in which biasing, forward or reverse, the depletion layer increases? Very good, Ayushi VI characteristics and graphs. Okay. In which biasing depletion layer increases, forward or reverse? Very good, Veena. Reverse. Shishani, in forward biasing, depletion layer decreases. Clear? Okay. So now I will move further. So today we are going to start with rectifier. Okay. So before starting with the rectifier, let's do a few questions of previous class. Let me do that. Okay. This is the question that you should solve. This is a very easy question. And just tell me which formula we are going to use here. Just tell me the formula. I will solve it, but you should tell me the formula. The question says pure silicon at 500 K has equal number of electrons and holes. That means if it has equal number of electrons and holes, concentration of this. Equal number of holes and electrons, that means Ni, that is intrinsic concentration is given, that is 1.5 into 10 raised to the power 16 per meter cube. This is the density, or you can say concentration. Ne into NH equals to Ni square. Very good. Very good. So now doping by indium. After doping by indium, they are saying that number of holes becomes 4.5 into 10 raised to the power 22 per meter cube. One thing they are asking the doped semiconductor is of. One is they are asking whether it's a P type or N type. So one thing is for sure that it is doped with indium. And this indium is of 13th group. That means trivalent impurity. And another thing you can see that number of holes are increasing. Number of holes are increasing. That means the semiconductor will be of P type. So two options are already wrong, which includes N type semiconductor. Now we need to calculate. So what we know that Ne into NH is equals to Ni square. Just put the value. So Ne is equals to, I put the value of Ni, that is 1.5 into 1.5 into 10 raised to power 16. If you square it, it will become 32 divided by NH. NH is what? 4.5 into 10 raised to the power 22. So if you solve this, decimal can be cancelled. Decimal can be cancelled. It will be 3. And if you solve it again, it will be 0.5. So that is 0.5 into 10 raised to the power 10. But if you write it in this format, it will become 5 into 10 raised to the power 9 per meter cube. So which option is correct? I think option A is correct. Clear? Okay, so this is the question, very basic question. Next question, tell me just one more question. After we will start with rectifiers. Okay, look, this question you should answer. The increase in the width of depletion region in a PN junction diode is due to forward biasing, reverse biasing, both forward and reverse, or increase in forward current. Which option, according to you, is correct? Option B with a question mark. Chichuni is saying option B. Veena is saying option B. Okay, very good. आपकी बात मान लेते हैं हम. Option B is absolutely correct. Because in reverse biasing, I asked you earlier, na, at the time of the start of the class, that in reverse biasing, depletion layer increases. So that's a simple question. So right now, you can solve one more question before moving to the class. In forward current, when forward current increases, in that case, the depletion region decreases. Forward current decreases, that means if you increase the extra potential, you know that while biasing, you can see there, let's see, in the biasing, I will delete this. This is P, this is N. If you forward bias it, and forward current increases means you are increasing this applied potential. You are increasing this applied potential. If you increase this applied potential, then depletion region will further shrink, it will decrease. So that's what the meaning of forward current increasing. You know the characteristics of VI characteristics. That was the VI characteristics, no? If you increase the potential, then current will increase. So if current is increasing, that means depletion region is decreasing. Okay. So now this one more question only. The given circuit has two ideal diodes connected as shown in the figure. The current flowing through resistor R1. This is R1. They are asking current in this resistor. Two diodes are connected this way. Now, one thing, they are ideal diodes. I have told you yesterday that ideal diode in forward bias behaves as a closed switch and in reverse bias behaves as an open switch. So first of all, you need to identify, let's suppose this is diode D1, this is diode D2. Which diode is forward bias? Tell me, which diode is forward bias? Either D1 or D2. D1 or D2, which is forward biased? Can you answer this? D2 is forward biased. Chichune is saying D2 is forward biased. Veena is also saying the same thing. Very good. You know that this is battery's high potential terminal, this is low potential. So this is high, this is low, this is high, this is low. So diode D2 is forward biased. D1 is reverse biased. This is forward biased. So this complete circuit can be redrawn in this way. This is our battery. And this diode will behave as open circuit because it is reverse biased, open switch. And this diode will behave as a closed switch because it is forward biased. Now there is a resistor in it as well, which is of 2 ohm. This is of 2 ohm. This is of 10 volt. Now you can clearly see that this complete circuit is a series circuit. So I is equals to V over R, and R is what? R equivalent. V is 10 volt, and the total resistance of the circuit is they are in series. So 2 plus 2, that is 4. So it will become 2.5 ampere, which is option number A. I think this concept is also clear. Now moving towards the rectifier thing. If we move towards the rectifier thing, this is rectifier. Okay. What are rectifiers? Rectifiers are the devices that converts bidirectional current into unidirectional current. Mark the word bidirectional current into unidirectional current. Let's suppose this is a bidirectional current. This is a bidirectional current, which is sometimes you called as AC. And it converts it into a unidirectional current like this. This is the rectifier. One thing is clear. Very good, Balveer Jha. Okay. Moving further, half wave rectifier. If I see what is half wave rectifier, then you can see that this circuit belongs to the half wave rectifier. I will tell you the punchlines after that. So first of all, there is a diode. Let's suppose this is a diode. This part is a transformer. This is the input supply that we are giving. This is the transformer. This is the load resistor. Now, what happens? You can see that if input is given as AC input or bidirectional input, this cycle is belongs to positive half cycle. This is negative half cycle, positive half cycle, and negative half cycle. So what I'm saying, in the first half cycle, let's suppose in the first half cycle, let's assume that A is positive. Then B will be negative. If A is positive, then B will be negative. If A is positive, then diode D will conduct. And I will write these conditions in this graph as well. I am saying in the first half cycle. In which cycle? First half cycle. A is positive, B is negative. Then diode is what? Forward biased. If diode is forward biased, then current will pass through it from P to N region. Then current will pass from P to Q. P to Q. That means in the first half cycle, there is a current in the direction P to Q. But in the second half cycle, if I talk, this time A will be negative and B will be positive. The polarity changes. The thing you know that polarity changes in the alternating supply. So let's suppose A is negative, then B will be positive. A is negative, B is positive. Then diode will be reversed biased and no current will flow. Current is zero. So what we get after this, the result of this is very simple. What is the result? In the positive half cycle, diode conducts. In the negative half cycle, diode doesn't conduct. In the positive half cycle, yeah, another half cycle, diode will again conduct and then again zero. So that's why it is called as half wave rectifier. It is called as half wave rectifier. This is a very simple thing. Now, one more important thing that you should remember as a punchline, and that punchline is, if the frequency of this is input signal, this is our output signal. If frequency of input is f, then frequency of output will also be f. This is the punchline that you should remember. If input signal has a frequency f, then output signal will also have a frequency f. Mark this word. This is the most famous question of rectifier, of half wave rectifier, I think. Okay. Moving further for full wave rectifier. Full wave rectifier, what we have changed? We have changed the circuit. There are two diodes used now, D1 and D2. And this is central tapped full wave rectifier. This is generally called as central or center tapped full wave rectifier. So whenever you see the name center tapped, then don't get confused. Let's suppose this is A, B, this is point C, and this is point D. Now again the same thing happening. There is an input signal like this. This is our input signal. Now this is positive half cycle, negative, positive, negative. What I am saying, in the first half cycle, let's suppose A is positive, then B will be negative. So I am writing this first half cycle, A is positive, B is negative. If A is positive, B is negative, then which diode is forward biased and which is negative, which is reverse biased? Which is reverse biased, which is forward biased? Okay. Can you find it very quickly? D1 forward biased. Very good. Okay. So D1 will be forward biased D2 will be reverse biased. If D1 is forward biased, that means current will start from this direction, in this direction. After reaching point, okay, this is already mentioned as P. So I am not writing this point C and D. This is P and Q mentioned already. Okay. So current after reaching point P will not go towards D2 because this will behave as an open switch. So current will move from P to Q. Direction of current is P to Q. In the second half cycle, what will happen? A will become negative, B will become positive. A will become negative, B will become positive. And if A is negative, then D1 will be reverse biased. This is very simple situation. This is forward biased. And this time D2 is forward biased. Again, current start from this direction, reach the point P, will not go towards A. Why will not go towards A? Because this is open switch. So it will go again from P to Q. That means in both the positive and negative cycles, current is along the same direction. Current is along the same direction. That means we can draw the output waveform in the positive half cycle. Which diode conducts? D1 conducts. In the negative half cycle, current is in the same direction. Which diode conducts? D2 conducts. Again, D1 will conduct and again D2 will conduct. Very good, Sam. Frequency is going to be 2F. Very good. So in this situation, again the punchline is, if frequency of input signal is F, then output signal will have a frequency 2F. Very good. Very good, Balveer. D1 forward, D2 reverse. I think this point is clear to everyone. Moving further. Zener diode. There are some special purpose diodes. Special purpose diode, the diode which are designed for some special purpose, out of which the most important diode is Zener diode. It is designed to operate in reversed biased. It is designed to operate in reverse bias. This is not the only thing. It is also designed to operate in the breakdown region. What is the breakdown region? I told you that in the VI characteristic graph, that at a certain time, at a certain voltage, in reverse biasing, the current suddenly increases. That region is called as breakdown region. So it operates in that region. So what are the qualities of this Zener diode? One quality is they are heavily doped. Mark my word, they are heavily doped. Doping means the amount of impurity you are adding. They are heavily doped. Another point. It is designed to operate in reverse bias without getting damaged. They will not get damaged if you work them or if you operate them in the reverse bias condition, in the breakdown region. The breakdown is Zener breakdown in these diodes. There are two types of breakdowns. One is avalanche, one is Zener. So the Zener diode works on the basic or on the properties of Zener breakdown. Remember the word, it's not going to be important topic for you. What is Zener breakdown? You should remember the name only. And this is not a difficult one to remember. In forward biasing, they behave as a normal diode. No problem in that. It's not like that they will only work in the reverse biasing mode. They can work normally in the forward biasing as well. Now, symbol of Zener diode. This is the symbol of Zener diode. What's different? This straight line is now converted to something zigzag kind of line. So don't worry. Somewhere you can see that this line is drawn in this way as well. So no worries with that. It can be drawn in any way, but it should be a zigzag kind of line. Moving further. I think till now every point is clear. What is VI characteristics of GR and Zener diode? Look at that. In the forward biasing, they are similar to normal diode. In the reverse biasing, the point to be noted is, if you see the reverse biasing, they are behaving like same diode, but in this region, this is called breakdown region. In this region, they will not destroy itself. They will work properly. One thing. Another thing that you can notice, this is current. Current is increasing without any change in the voltage. And this voltage is called as Zener voltage. This voltage is called as Zener voltage or breakdown voltage. Remember the word. This voltage is called as breakdown voltage. And for a Zener diode operating in Zener voltage or breakdown voltage, its potential will not increase further. It will remain constant at this point. It is mentioned here. In the breakdown region, the voltage across the diode remains constant and is known as Zener voltage. Zener voltage or breakdown voltage. Now, this principle of Zener diode, this characteristic of Zener diode is used in making voltage regulators. So Zener diode are used as voltage regulators. This is an important question. This is a voltage regulator. Now, let's understand it. What kind of questions they will ask you? One thing is, voltage regulator is a device which gives constant output. Which gives constant output voltage. Irrespective of the fluctuations in the input, if your input voltage is fluctuating too much, but output voltage will remain constant. That's what voltage regulators. What happens? This is a Zener diode. In parallel to the Zener diode, there is a load resistor. Load resistor is something along which or in which you are taking the output. It may be a bulb, it may be a fan, it may be something else. Like any device, it can be. So this is the load resistor along which we are taking the output. So what happens here? We know that in reverse biasing mode, the potential across the Zener diode will remain constant. Whatever you do, the potential across the Zener diode will remain constant. And if it is so, then potential, this is in parallel. You can see that this load resistor is in parallel. If this load resistor is in parallel, that means potential will remain same. That means output of this load resistor will also be Vz. I think this point is clear now. Why I am talking about this point? This is very important point. The load resistor is connected in parallel. So if someone says that a Zener diode has a Zener voltage or breakdown voltage of 10 volt, let's suppose Zener diode has a breakdown voltage of 10 volt, then what will be the output? You will say output will also be 10 volt because output resistor is connected in parallel. Okay. So where does the fluctuations go? If our input is fluctuating, input voltage is increasing, then where does that fluctuation go? This fluctuation is tolerated by this series resistor. This is called as series resistor. And this fluctuation is tolerated by this series resistor. Is this point clear? Now, listen to me very carefully. I will give you an example. What are the type of questions they may ask? One type of question they will ask you. I am not describing the theory here. It is not important. What type of question they will ask you? The output voltage. First type of question, they will ask you the output voltage. Output voltage is nothing but Zener voltage. One point is clear. Second question that the examiner may ask is the current in Zener diode. Second, in output resistor, that is RL, or in series resistor R. He can ask, or he or she can ask, the current in all these three elements: output resistor, series resistor, and Zener diode. So to solve this kind of problem, I will give you an example. Let's see. Let's go to the example directly. Let's go to the example directly. This is the example. Okay. So read the question, and this is the most important question of Zener diode. Very important question. You will learn the concept, then it will be very good. Again, you can see there is a Zener diode. Just tell me which is the load resistor out of which 250 ohm or 1 kilo ohm, which is the output resistor, which is the load resistor. Tell me out of this circuit, which is the load resistor. Can you identify the load resistor in this diagram? Let's suppose this is R1, this is R2. Which is load resistor? 1 kilo ohm. Very good, Veena. 1 kilo ohm. How to identify the load resistor? The resistor which is connected in parallel with the Zener diode. This is Zener diode. Okay. Now question says, a Zener diode having breakdown voltage equals to 15 volts. That means the voltage across it is 15 volt. Is used in a voltage regulator circuit shown in figure. The current through the diode is. So they are talking about the current in this circuit, in this diode only. They are not talking about the current in anywhere else. Okay, let's solve it. First of all, I will assume that there is a current I in this resistor. This is 20 volt battery, na? So this is current I. After reaching this point, current will divide in two parts. Let's suppose I1 goes there and I2 goes there. Clear? Till now, every point is clear, I1 and I2. Very good. Very good, Balveer. Okay. Now, can you identify that 20 volt is applied as the input, out of which 15 volt is required for the Zener diode? So remaining is 5 volt. So 5 volt will be along this series resistor. Is this point clear? There is a total potential applied is 20 volt, out of which 15 volt is dedicated for the Zener diode. So the remaining 5 volt is tolerated by this series resistor. And because they are in parallel, so 15 ohm will also be there. Clear at this point? Now, you know the potential across each resistor. 5 volt and 15 volt, you know the resistance value. Can you solve the current here? If I say, at this point, if you see, apply KCL, Kirchhoff current law, then you can clearly see that I is equals to I1 plus I2. Clear? And we need to calculate I1. So I1 will be I minus I2. Let it be equation number 1. So now I am going to calculate I and I2. If I calculate I is the current in this 250 ohm resistor. I is equals to, from Ohm's law, V over R. Potential is 5 volt. Resistance is 250. That will be 1 by 50 ohm, if I am not wrong. 1 by 50 ampere. Similarly, if I talk about this current, I2 will be, potential is 15 volt. Resistance is 1 kilo ohm, that is 1000. If you divide it by 5, it will become 3 by 200 ampere. Now put this value in equation 1. From 1. If I put the value, so I1 will be 1 by 50 minus 3 by 200. Can anyone tell me the answer after solving this? You should be quicker than me in solving this equation. I1 will be 1 by 200. If I solve it 1 by 200, can I write it as 1 by 2 into 10 to the power 2? 1 by 2 means 0.5 into 10 raised to the power minus 2. So that will be 5 milliampere. 5 milliampere, which is option number A. 5 milliampere. Very good, Balveer. That's very good. I think this question is clear. This type of question is clear. In this question, we have learned all four things to calculate. What are the four things? The output voltage, we have calculated 15 volt. The current in all these three quantities, three elements we have calculated. So I think that Zener diode question is clear, and they are the most asked questions. Okay, this diagram you are asking now. Okay, I will delete everything from here and explain it again. Okay, so let's start again. This is the circuit. Now, for a voltage regulator, listen to me, they are used to work as a voltage regulator circuit. If it is working in voltage regulator, then it should be reversed biased. Is this point clear? For reverse biasing, you can clearly say that the battery should be something like that. This is 20 volt, this is 0 volt. Clear? This is the battery. Current starts from the positive terminal. So current is starting from here. Let's suppose current here is I. After reaching this point, current will divide in two parts. Let's suppose I1 goes there and I2 goes there. Is this point clear? Now, another thing is the potential across this Zener diode is given as 15 volt. But we have applied only 20 volt. 20 volt I have applied and 50 volt is along this 15 volt. Then remaining 5 volt will be along this. So we got the potential across this resistor. And this 1 kilo ohm is in parallel with the Zener diode. So 15 volt will be along this because in parallel combination, potential remains same. Is everything clear now? What are the things? Now, in the first part, we have applied Kirchhoff current law, or you can say junction law, which says current entering the junction is equals to current leaving the junction. Very good, Chichni. I think it's clear. Okay. Moving further. Now there is few more, what I say, special purpose diodes. Okay. So next is photodiode. Photodiode, I will say this is a simple device, simple diode, which is used to detect the presence of light. The statement should be clear. It is used to detect the presence of light. How it look like? In this, a PN junction, this is a similar PN junction, normal PN junction, but the thing is, near the junction point is made transparent so that light can enter it. Now, first point is clear. It is used to detect the presence of light. Next is, it operates in reverse biasing. This is again a very good concept. It operates in reverse biasing. Zener diode is also working in reverse biasing. Photodiode is also working in reverse biasing. Next point. The incident light photons must have higher energy than the band gap. Now, this point you will not remember. I will tell you how to remember that. What will happen actually. Till now, what you know, that in reverse biasing, there is a very small amount of current. Clear? In reverse biasing, there is a very small amount of current, and that current is due to minority charge carriers. Till now, every point is clear. Now, what will happen if light is incident on the junction and the light has energy greater than the band gap? You know the band gap thing? This is conduction band and this is valence band. You know this thing? Valence band, conduction band. And the electrons in the conduction band are called free electrons. Only they will conduct. And the holes in the valence band will conduct. So if the light is incident and light has more energy than the band gap, then it will break some bonds. And some electrons and holes are created. So for this to happen, the incident energy must be greater than the band gap. So that's what mentioned here. The incident light photons must have higher energy than the band gap. Now I think it is clear why it should have higher energy than the band gap, so that bonds can be broken. Now, what happens? In the reverse biasing, if I have applied no current, I have applied no light is incident, then there is a very small amount of current, and this current is known as dark current. Now, if I gradually increase the intensity of light, increase the intensity of light, what will happen? If I increase the intensity to I1, then current in the reverse bias will increase. If I further increase the intensity, then current will further increase. Why current is increasing on increasing the intensity? Because more intensity means, complete the sentence, more intensity means, complete the sentence. Now I am on a perfect standby mode. On increasing intensity, complete the sentence. Okay, more current. Now, this is the final output answer you are giving. What is the meaning of more intensity? More intensity means more number of photons are coming. More intensity means more number of photons are coming in the light. This point should be remembered by everyone. More intensity means more number of photons are coming. If more number of photons are coming, that means that more collision will happen and more electrons will break bonds. So that's why current is increasing. So in this diagram, I will say I1 is greater than I2. So punchline to be remembered, it operates in reverse bias. Second punchline is energy of the photon should be greater than band gap. Clear? Okay, moving further. LED. LED is again a very simple concept. More frequency means more kinetic energy. Balveer, very good. More intensity means more number of photons. Very good, Balveer. You are doing a great job. Your preparation is going good, I think. Very good. LED. LED, one thing to be remembered, it operates in forward biasing. Now, let me explain you a few things here. Let me explain you. Give me a 1 or 2 minutes time so that I can explain things here. This is a P, this is a N region. In this region, holes are there. In this region, electrons are there. I think this point is clear. Now, when I forward bias this junction, what will happen? Listen to me very carefully till now, at this point of time. Everything will be crystal clear. Now, when I forward bias this, then these electrons will enter the N region. They will move this direction and holes will move in this direction. Why they will move in this direction? Because this battery will create a field like this. And negative charge moves opposite to the field and positive charge moves in the direction of field. So they will meet each other. Now the thing is that, listen to me, electrons are in the conduction band. They are in the higher energy bond, higher energy level. Holes are in the lower energy level. They are in the valence band. And electrons are in the conduction band. So when they meet with each other, that means electrons are making transition from higher energy to the lower energy. So in the atoms chapter, what we have learned, that when electrons comes from higher energy to lower energy, it releases some energy. It releases some energy in the form of photon. So now what I am saying, when this recombination happens, some energy is released in the form of photons. Sorry. Some energy is released in the form of photons. Now, in normal diodes, like in silicon and germanium diodes, this emitted photon lies in the infrared region and just creates heat, lies in the infrared. So what I'm saying, there happens a recombination of what? Electrons and holes. And due to this recombination, energy is released. This energy lies in which region? Infrared region, which causes only heat. Now, if I design some material like that, in which the released energy lies in the visible region, then we will get the LEDs. So LEDs are made from certain materials to get the desired color, because energy is going to be released, photon is going to be released due to the recombination. But if I arrange that photon in a region, so that's why we have used some materials as a LED material like gallium arsenide, gallium phosphide, gallium arsenide phosphide. By varying the amount of these compounds, we can change the color of the LED, that which color is going to be emitted. This is a very complex thing, but right now these LEDs are in the market for 1 or 2 rupee cost, or I think 5 rupee cost. But this is a complex thing to achieve at the R&D time. Now it's very cheaper. What I'm saying, that these are the frequently used material for LED. Is this point clear? So who is responsible for the emission of color? For the emission of color, the recombination of electrons and holes are responsible for that. Clear? Okay. Now we are moving towards the AND gate or logic gates part. Should I move now? Okay. So logic gate parts, if I talk about one important aspect of that, there will be, I think, 5 gates that we are going to study. First is AND gate. What is AND gate? You should remember the output here. Output will be high. Okay. In digital electronics, let's talk about, there is only two things. One is low, one is high. Low is denoted by 0, high is denoted by 1. That's all. This is all digital electronics, you will say. Low is 0, high is 1. So what is output will be high only when all inputs are high. जब सारे इनपुट हाई होंगे तब ही आउटपुट क्या हो सकता है? हाई हो सकता है. हाई का मतलब 1 हो सकता है. So if I put the values here, A and B, this is AND gate symbol. These A and B are input. This is output. I can take the value 0, 0, 0, 1, 1, 0, 1, 1. Only these 4 combination can be formed for inputs. So whenever the A and B inputs are 0, the statement says output will be high only when all inputs are high. So in the fourth, this one, all inputs are high, so output will also be 1. In all other cases, at least one input is 0. That means output will also be 0. Is the statement clear? So in AND gate, you will remember one thing, that when the output is high, when both the inputs are high. This is the truth table. This is called as truth table. Next gate is OR gate. See the difference in the symbol. In AND gate, this line is straight. This line is straight, you can see. And in OR gate, this line is curved. Clear? So this is the variation. Variation in OR gate is as output will be high if only one input is high. One input is high. If out of two inputs, any one input is high, then output will be high. So let's make a table. What are the possible combinations? 0, 0, 0, 1, 1, 0, 1, 1. What will be the output? This is going to be 0 because all the inputs are 0. In all other cases, it will be 111. Why 111? Because at least one is high. OR gate, कोई एक भी 1 होगा तो output 1 होगा. Very good. So now there comes another gate, which is a very simple gate, your favorite, NOT gate. What it does, it reverses the input given. If you give 0, it will give 1. If you give 1, it will give 0. This is single terminal device. single terminal, and all the previous one are two terminal devices. They are two terminal devices. Two terminal because there must be two inputs A and B. There must be two inputs. But in NOT gate, there is only one input. Now there is a NAND gate. NAND gate is nothing but AND plus NOT gate. Now, if I tell you the truth table, you can see the symbol here. There is a symbol of NOT. This dot represents NOT. And this is AND. So AND plus NOT is called a NAND gate. Again, inputs are same 0, 0, 0, 1, 1, 0, and 1, 1. Clear? So the output of AND should be reversed in the NAND gate. So output of AND is this is 0. This is going to be 0. But in NAND gate, it will become 1, 1, 1, and 0. Very good. And is A into B or is A plus B? Very good. Is this thing clear? What happens? Just reverse the output of AND gate. In the same way, there is a NOR gate. I will not take a lot of time. 0, 0, 0, 1, 1, 0, 1, 1. What if I say the output of OR gate is 0, 1, 1? So it will become 1, 0, 0. 1, 0, 0. Very good. So now after solving this, I will give you a question based on this. I will give you a question based on logic gates. Let's solve this question. Okay. So answer me. Balveer. Answer this question. Veena, Chichuni, and Gauri is there or not? Gauri, you are not answering anything today. Nisha, Gauri, Priyadarshini, Sam, Logesh is not there today. Okay. Everyone should participate now. Okay, answer. I'm waiting for your answers. There was a net issue. Okay, Gauri. So I'm waiting for the response. I will explain this to you. Okay. So first of all, identify the gates. This is OR gate. You can identify this is AND gate. So one thing to be very clear, if I tell you output of AND gate, the question says that to get output 1. That means here the output should be 1. That means high output. For output to be high, what we know that in AND gate, both the inputs should be high. That means this should be high and this should be high. Is this point clear? Both these should be high. If both of them should be high, then one thing is sure that C is going to be 1. Option B, very good. C is going to be 1. Or from the option point of view, I can clearly see that C is 1 in only B part. So we got the answer. We got the answer. Now this is OR gate. Very good. Vana is also saying B. Very good. Chichuni is saying B. Balveer is saying B. Very good. So option B is clear. Now to get the output of OR gate as 1, what we should do? We must have either one of the input as 1. So in the option A is given as 1, B is given as 0. What are the other possible combinations here for A and B? A and B should be 1 and 1 as well, 0 and 1. All these three possibilities are there for A and B. But C must be 1. C must be 1. Okay. Name is Das. Okay. Das. Okay, tell me in this question, the given electrical network is equivalent to what? Is it equivalent to OR gate, NOR gate, NOT gate, and AND gate? There are four options, and this is the given circuit. Are you doing it? Okay, someone has answered. Chichinu is saying option B is correct. Option B, that means NOR gate. Okay, let's find out. Okay, first of all, what we will do, I have mentioned the inputs. The possible input values are this 0, 0, 0, 1, 1, 0, and 1, 1. Now, this is NOR gate. So we can get the value of y1 very easily. This is NOR gate. If it is NOR gate, then value of y1 will be. Can anyone answer what is the value? What are the values of y1? That is 1,000,000. Is this point clear? This is NOR gate. So what are the values of output of y1? That is NOR gate output. That is 1,000,000. Now, this is again a NOR gate. This is again a NOR gate. Now, in this situation, what will be the output for NOR gate? Can you see that both the inputs of this NOR gate are same? Both the inputs are same. You can clearly see that. If both the inputs are same, then if I say, if both the inputs of NOR gate are high, then output will be low. That is 0. If both the inputs are low, then output will be high, high, high. 0, 1, 1, 1. Okay, very good. Now, this is the NOT gate. This is the NOT gate. So output of NOT gate is nothing but reversed. Just reverse the thing. That is 1,000,000. Now what you need to think about, that for these inputs A and B, final table is A, B, and Y. That is 0, 0, 0, 1, 1, 0, 1, 1. And this is 1,000,000. Now which gate it should be? Which gate it should be? Someone has answered B. Veena is saying B. It is NOR gate. Okay. Anyone else? Low inputs are giving high output. Okay. You can clearly see that low inputs are giving high output, and this 1,000,000 is stable for the NOR gate. And I think who has answered it? I think Veena has answered correctly. Veena, your answer is correct. And nobody else has answered. Balveer is saying NOR gate. Very good. So the correct option is NOR gate. I think everything is clear now. One more kind of question that may be asked in this gate thing is using waveforms. So from the P by Qs, you can practice those kind of questions. And from my side, it's the end of the session. Okay. So bye everyone. In the next class, I think tomorrow is your test now. Bye everyone. Bye. Bye Das.